There is a planet next door to us, almost exactly the size of Earth, made of almost exactly the same material, sitting in almost exactly the same slice of the solar system where life figured out how to happen. And it is spinning the wrong way, not tilted, not wobbling, reversed, so slowly that a single day on its surface outlasts an entire year on Earth. 60 years of physics have failed to explain it, and tonight we walk through every hypothesis on the table, including the ones researchers will only discuss in whispers. If you are new here, welcome to Sundown Science. Hit like, subscribe, and get comfortable, because tonight I am going to walk you through the reason Venus, our supposed twin, is spinning in the wrong direction, and why 60 years of physics still cannot fully explain it. Settle in, and let's ease into this one slowly. The wrong direction next door. Venus is, by every external measure, Earth's twin. The mass comes in at about 81.5% of Earth's mass, which in planetary terms is basically a rounding error. The radius is 95% of Earth's radius, meaning if you shrunk our planet down by 5%, you'd get Venus. The density is nearly identical. The rocky, iron-cored composition matches. Both worlds formed from the same inner disk of the same protosolar nebula 4.5 billion years ago, in the same relative neighborhood, pulling in the same kinds of dust grains and metal fragments and volatile pore silicates. If you were a chemist sampling the initial conditions, you would not be able to tell these two planets apart at the starting line. You would predict that they would end up doing the same kinds of things. You would predict, in particular, that they would spin the same way, because spin is something a planet inherits from the cloud it condenses out of, and they condensed out of the same cloud. This is not a guess. This is physics. Angular momentum conservation is one of the most reliable laws we have. When a rotating cloud collapses into smaller objects, those objects inherit the rotation, and yet, Venus turns clockwise. Viewed from above the North Pole of the solar system, looking down at the flat plane where everyone dances, every planet except Venus is rotating counterclockwise. Earth, Mars, Jupiter, Saturn, Neptune, Mercury, they all spin in the direction the original disk was spinning. Venus alone has decided it's not doing that, it's going the other way, and this is not a subtle offset. This is not a minor axial tilt. This is a full reversal. The planet rotates opposite to its orbit around the Sun, which means if you were standing on Venus, watching the Sun come up, it would rise in the west and set in the east, completely inverted from our experience on Earth. This is not a decorative detail. This is a first-order rule violation, which is science speak for saying that the simplest, most basic prediction the theory makes about this object turns out to be wrong. And then it gets worse, because Venus doesn't just spin backwards. Venus spins slowly, in a way that human brains genuinely cannot process without sitting with the numbers for a while. A single rotation of Venus relative to the stars takes 243 Earth days. A single orbit of Venus around the Sun takes 224 Earth days. Stop and look at those two numbers. The day is longer than the year. Think about what that means. If you lived on Venus and you were somehow measuring a day as one full rotation on its axis, that day would outlast a full trip around the Sun. The concept of a year, as we understand it on Earth, completely breaks down. Venus finishes its lap around the star before it finishes turning around once. Your calendar would have to be inverted. Your sense of how the heavens work would have to be rebuilt from scratch. Then there's the axial tilt. Earth sits at about 23.5 degrees, which is why we have seasons and why the poles get weird light patterns. Venus sits at 177 degrees. That's 3 degrees shy of being perfectly upside down. You can look at that two ways, and physicists argue about which framing is more honest. You can say Venus has a tilt of almost 180 degrees, meaning the planet has been flipped over, and it still rotates in the original inherited direction relative to its own body. But because the body has been inverted, from our vantage point, it now looks like it's spinning backwards. Or you can say the tilt is essentially zero and the rotation itself has genuinely reversed. These two descriptions sound like they're describing the same outcome, and geometrically they are, but physically they imply very different histories. In one version, something turned the entire planet upside down. In the other version, something gradually dragged its rotation to a stop and then reversed it. These are not the same story, and we cannot currently tell them apart. This is the anomaly you have to sit with before any explanation will make sense. Venus should rotate the same direction as Earth, because it formed from the same material in the same way under the same physical laws. Venus should rotate at a reasonable speed, somewhere in the range of a day or so, because planets that small and that close to the Sun don't typically grind their rotation down to near stopping over their lifetimes. Venus should have a normal-looking axial tilt, because catastrophic reorientations of planetary bodies require catastrophic amounts of energy, and Venus is not doing any of those things. It's doing all three of them wrong at once. The statistical framing here is important. When you look at the 8 planets in the solar system, 7 of them rotate prograde, meaning in the original direction of the disk. 1, Venus, does not. Uranus is sometimes thrown in as a fellow rebel because it's tilted about 98 degrees, meaning it's basically rolling on its side. But Uranus is not truly retrograde in the way Venus is. Uranus is tipped over. Venus is inverted. These are not equivalent anomalies, and anyone who tells you they're the same thing is skipping over the details. Venus stands alone. Venus is the single data point in our solar system that violates the most basic prediction of how a planet should behave if it formed the way we think planets form. And you have to ask, genuinely ask, how does something like this survive the process of getting made? Formation physics is, in principle, deterministic. You put gas and dust in a rotating cloud, you let gravity pull it together, you wait for it to cool and settle, and what you get is a set of objects rotating in the direction the cloud was originally rotating. That's the default. That's the path of least resistance. Venus is not taking the path of least resistance. Venus is taking a path that, under normal physics, shouldn't be available. Something overwrote the initial conditions. Something took whatever Venus was supposed to be and turned it into what Venus is now. We're going to spend the rest of this conversation trying to figure out what that something was, and I want to warn you now, there is no clean answer waiting at the end. There are multiple candidates, each with strengths, each with problems, and the one thing they have in common is that the evidence that could tell them apart has been systematically erased by Venus itself over billions of years of volcanic resurfacing and atmospheric chaos. So let's start with what we know about how planets are supposed to work. The solar system's default setting. To understand why Venus is strange, you have to understand what normal looks like. And normal starts 4.5 billion years ago with an enormous, slowly rotating cloud of gas and dust drifting in a corner of the galaxy. That cloud was mostly hydrogen and helium, seasoned with traces of heavier elements from previous generations of stars that had exploded and scattered their guts into space. For a long time, nothing much happened. Then something perturbed it, possibly a shockwave from a nearby supernova, possibly just an internal instability, and the cloud began to collapse under its own gravity. As it collapsed, a tiny initial rotation, the kind of drift that any cosmic object has just by existing, got amplified. Angular momentum is conserved, which means when the size of the rotating thing shrinks, the speed of the rotation has to increase to compensate. The cloud went from a slow, lazy turn to a whirling disk, and the disk flattened out the way pizza dough flattens when a chef spins it in the air for exactly the same reason. At the center of that disk, hydrogen piled up until the pressure was enough to ignite fusion, and the sun switched on. Around it, the leftover material, now a flat disk of gas and dust orbiting the new star, began to clump. Dust grains collided and stuck. Clumps hit other clumps and built larger clumps. Over millions of years, those clumps became pebbles, then boulders, then asteroid-sized bodies, then planetesimals the size of moons, then protoplanets the size of Mars. And crucially, all of this happened inside the rotating frame of the disk. Every object being formed was inheriting the rotational motion of its parent cloud. When two rocks orbiting the Sun collided and merged, the merged object kept rotating in roughly the direction the rocks had been moving, which was the direction of the disk. This is why, when we look at the solar system today, we see such a powerful pattern. The Sun rotates in one direction. The planets orbit the Sun in that same direction. Most of the moons orbit their planets in that same direction. Most of the planets rotate on their own axes in that same direction. The asteroid belt moves in that direction. The Kuiper belt moves in that direction. Everything, almost everywhere, is pointing the same way because everything came from the same originally rotating cloud, and nothing fundamental has happened to change that inheritance. This is what we mean when we say prograde. Prograde is the default. Prograde is what you get when nothing interesting happens. Prograde is the fingerprint of the disk printed onto every object born out of it. Retrograde, the opposite direction, is not something you get by accident. Retrograde requires a story. It requires something to have come in and disrupted the inheritance. It requires an intervention. This is why retrograde moons in the solar system, the few that exist, are almost always interpreted as captured objects. Triton, the big moon of Neptune, orbits retrograde, and the leading explanation is that Triton didn't form around Neptune at all. Triton was a Kuiper belt object that got too close and got pulled into orbit from the outside, which is why it moves against the grain. When we see retrograde motion, we assume an origin story that involves something being brought in from elsewhere or something violent happening. Now, why does this matter for Venus? Because Venus is a planet, not a moon. You can't tell the story where Venus was captured from somewhere else, because a planet this big, this close to the Sun, with this kind of composition, doesn't just drift in and park itself. The orbital mechanics don't really support that. So if Venus is rotating retrograde, and Venus formed where it sits now, then something happened to Venus after formation. Something rewrote the fingerprint of the disk. Something took a planet that should have been spinning prograde, like everybody else, and either turned it over, slowed it down, and reversed it, or both. Changing a planet's spin is not easy. I want to emphasize that, because it's easy to say the words and breeze past them. Reversing the rotation of an object with the mass of Venus takes a truly staggering amount of energy. You can do the math, and people have, and the numbers come out looking like the energy released by entire sequences of catastrophic events stacked on top of each other. A planet's spin is, in a very real sense, its most stable property. Its orbit can be nudged, its orbit can be migrated, its orbit can be changed by tugging gently over long periods. But its rotation? Its rotation is a fossil. Its rotation encodes the moment of its birth. Its rotation is supposed to remember. Venus does not remember. Or rather, Venus remembers something different, something none of the other inner planets experienced. Think of spin the way you'd think of a ring on a finger. The ring is stuck. You can slide it up and down, you can twist it, but taking it off requires real force. Now imagine someone took the ring off the hand, turned it inside out, and put it back on, and you're trying to figure out how they did it without anyone noticing. That's the Venus problem in miniature. Something took a planet's fundamental rotational signature and reversed it, and we cannot figure out what did the reversing, and we cannot find the fingerprints of the one who did it. So, the default expectation was clear. Venus should look like Earth. Venus should spin like Earth. Venus should have retained the same rotational inheritance as every other inner planet. and this expectation held for a long time, partly because of physics and partly because we couldn't actually see through Venus's clouds to check. For most of human history, we looked at Venus and saw a bright dot. Then, once telescopes got better, we looked at Venus and saw a featureless, creamy sphere. The cloud cover was total. The surface was invisible. Nobody could watch surface features rotate because there were no visible surface features. We assumed Venus was basically Earth, and we assumed Venus rotated basically like Earth because we had no reason to assume otherwise and no way to check. That's the situation that persisted until the middle of the 20th century. And then the situation ended, abruptly and unkindly, because a new tool came online, and the new tool could see through the clouds. The radar shock. The problem with studying Venus through a telescope is that Venus doesn't show you anything. It's wrapped in a permanent shroud of sulfuric acid clouds and high-altitude haze that reflects almost all the sunlight that hits it, which is why Venus is the brightest object in the night sky after the moon. You're not seeing a planet when you look at Venus. You're seeing a mirror. To actually see the surface, to see features rotating, to pin down how fast the thing was turning, you needed to cheat. You needed a wavelength of light that goes through clouds. And in the late 1950s and early 1960s, radar astronomy had finally matured to the point where that was possible. Before radar, the estimates of Venus's rotation period were all over the place. Some astronomers thought Venus was tidally locked to the Sun, meaning one face permanently pointed at the star, the way the Moon permanently points one face at Earth. If that were true, a day on Venus would equal a year on Venus, which would be strange, but at least internally consistent. Other astronomers thought Venus had a day similar to Earth's, about 24 hours, because why wouldn't it? A few thought the rotation was somewhere in between. The point is, there was no consensus. There was no data. Venus was a guess. Then, in 1961 and 1962, astronomers began bouncing radar signals off Venus and measuring how the reflected waves came back. The technique is elegant. You send out a precisely timed pulse of radio waves. The waves hit Venus, scatter off the surface, and return. Different parts of the planet return the signal with slightly different delays and slightly different frequency shifts, depending on how they're moving toward or away from you as the planet rotates. If you analyze those shifts carefully, you can extract the rotation rate. And when they did this, when Goldstein and others worked through the math with the data from Arecibo and Goldstone, the answer they got was not any of the answers anyone had been predicting. Venus was rotating slowly, not a 24-hour day, not tidally locked, something in between, but much closer to locked than to Earth-like. They measured a sidereal rotation period of about 243 Earth days, which was a shock on its own. But then they looked at the direction of the rotation, and that was the part that broke people. Venus was rotating retrograde, backwards, against the grain of the entire solar system. This was not what anyone had expected. This was not even on most people's list of possible outcomes. If you had surveyed planetary scientists in 1960, almost nobody would have put retrograde rotation as a serious possibility for Venus, because there was no physical reason to think a planet that had formed where Venus formed, from the materials Venus was made of, should have been going the wrong way. The measurement was confirmed, repeated, refined. By the mid-1960s, the result was solid. Venus rotates retrograde with a sidereal period of about 243 Earth days. Venus has an axial tilt of nearly 177 degrees. These were now facts, not hypotheses. And the planetary science community had to sit with those facts and figure out what to do with them, because they did not fit into any existing theoretical framework. They did not match predictions. They could not be waved away. In 1965, the astronomers Goldstein and Carpenter published one of the early influential discussions of this problem, and the quote that tends to get cited from that era is, more or less, that the only limit on explanations for Venus's retrograde rotation is the imagination of the theorists, which was a polite way of saying that nobody knew what had happened, and every idea anyone proposed was about equally bad, and the field was wide open for speculation. This is what paradigm disruption looks like. You have an observation that doesn't fit, and because the observation is solid, you have to break the paradigm rather than the observation. You have to go back and figure out how something you thought couldn't happen did happen. This is what I want you to sit with, this idea that spin should be a fossil, that spin should remember where the planet came from, and that Venus's spin has been overwritten so thoroughly that we can't read the original. That's the central thread of this entire story. Every hypothesis we're about to discuss is an attempt to identify the thing that did the overwriting. And within a few years of the radar discovery, the first hypotheses started appearing in the literature. The most obvious one, the one that's always the first reach when you see something anomalous, was impact. Something hit Venus, something big, something that flipped it over or spun it backwards or both. It was the sort of hypothesis that felt satisfying immediately because it's dramatic, it's visual, you can picture it, and it transfers the mystery from a physics problem to a historical one. What if a Mars-sized object hit Venus glancingly billions of years ago? Wouldn't that do it? Initially, people thought maybe. Then people ran the numbers. And the numbers started looking uncooperative. Because a late impact capable of reversing Venus's rotation would have to deliver a truly immense amount of angular momentum to the planet in the opposite direction of its existing spin, not just enough to slow it down, enough to stop it and reverse it. And an impact that big tends to do other things. It tends to liquefy the crust. It tends to blow off large fractions of the mantle. It tends to leave debris rings that should eventually reaccrete into moons, which Venus conspicuously lacks. So, impact was the first hypothesis, and it ran into walls almost immediately, which meant people had to think harder, and the thinking got stranger, and the paradox of Venus became one of the earliest and longest-running unresolved problems in modern planetary physics. We'll get to every one of the proposed solutions, but first we need to talk about what spin actually is, what it means, and why reversing it is such a peculiar thing to try to do. Angular momentum as cosmic memory. Spin is one of those things that feels simple until you look at it carefully. You see something rotating and you say, okay, it's spinning, fine. But underneath that observation is a conserved quantity called angular momentum, and angular momentum is kind of the unsung hero of cosmic physics. It's the reason galaxies are shaped like disks. It's the reason planets orbit instead of falling into stars. It's the reason ice skaters pull in their arms to spin faster. It's the reason the solar system looks the way it looks. Angular momentum, in very rough terms, is a measure of how much rotational motion a system has, combining how massive it is, how spread out the mass is, and how fast the rotation is happening. The key property, the one that matters for Venus, is that angular momentum is conserved. It doesn't just disappear. It doesn't just change. If you want to change the angular momentum of a system, you have to exert a torque on it from outside. Torque is rotational force. Without external torque, whatever spin a thing has, it keeps forever, until something acts on it. This is why the figure skater analogy is so useful. A skater spinning on the ice is an isolated system, roughly speaking. When she pulls her arms in, she's not adding any angular momentum. She's just redistributing her mass closer to her rotation axis. Because angular momentum has to be conserved, and she's reduced the spread of her mass, the only thing left to change is her rotation speed, which goes up. This is the same reason the collapsing protosolar cloud spun faster as it contracted. It had a set amount of angular momentum to keep, and as it got smaller, it had to turn faster to keep that amount. Now apply that to a planet. A planet is, once formed, a relatively isolated spinning object. It's not perfectly isolated. The Sun exerts tidal forces on it. Other planets perturb it gravitationally. But those effects are small, and over short timescales, they don't do much. Which means a planet's spin, once set at formation, should persist for a very long time. Not forever, but for a long time. For billions of years, essentially, if no major event intervenes. And this is what we see for most planets. Their rotation rates and directions can mostly be explained by their formation plus minor modifications over time. Venus is the exception. Venus's current spin cannot plausibly be its formation spin. It's too weird, it's too slow, it's too inverted. Something has altered Venus's angular momentum in a significant way. And because angular momentum is conserved, that something had to either transfer angular momentum into Venus from outside, transfer it out, or both. The magnitude of the change matters. We're not talking about tweaking Venus's rotation by 10%. We're talking about completely reversing it. In terms of angular momentum bookkeeping, that's a massive change. That's the kind of change that demands a significant physical cause. There are really only two broad ways to change a planet's spin that much. One is a single, rapid, violent event that delivers a lot of angular momentum very quickly, an impact, a merger, a catastrophe. The other is a slow, sustained torque that acts on the planet over geologic time, gradually bleeding angular momentum out of its rotation and eventually reversing it. These two categories of explanation have very different implications. The first implies Venus has a dramatic moment in its past, a specific thing that happened at a specific time. The second implies Venus has been quietly, slowly, boringly getting its rotation rewritten for billions of years by forces we can barely detect. And here's the catch, the thing that makes this whole problem so frustrating. Both categories of explanation can, in principle, produce the present-day state of Venus. A dramatic impact could have flipped it. A slow torque could have reversed it. The current observations are, to some extent, consistent with either history, which means the observations alone cannot tell us which history actually happened. We have to look for secondary clues. We have to look at the atmosphere, the surface, the isotope ratios, the gravity field, anything that might preserve a memory of the original event or the gradual process. And this is where we have to confront the spin memory problem head-on. The physical record of Venus's past is catastrophically incomplete. Venus has been resurfaced by volcanism, maybe all at once in some massive event around 500 million years ago, maybe continuously. Either way, there's no ancient crust. There are no rocks on Venus's surface that date back to its early history. Compare this to Earth, where we have zircons almost as old as the planet itself, preserved in tiny grains that have survived every upheaval the planet has thrown at them. Venus has nothing like that. Whatever geological record of its early rotation history might have existed has been cooked, melted, and buried. So we're left trying to reconstruct the history of a planet's rotation from physics alone, without the usual tools, without geology, without moons to serve as dynamical witnesses, without a preserved magnetic field record, just the current state of the system and the physics we can model, and the isotopic fingerprints we can sample from the atmosphere. It's like trying to figure out how a complicated Rube Goldberg machine was originally set up by looking at where the marble ended up. Any theory of Venus's rotation has to account for both the reversal and the slowdown simultaneously, and it has to be consistent with everything else we know about the planet. This is a much harder problem than it might look, and it's why so many hypotheses have come and gone over the past 60 years without any of them achieving consensus status. Every time someone proposes a clean explanation, someone else points out what it fails to explain, and the debate continues. But before we go deeper into those debates, I want to make sure we really understand what retrograde means and why thinking about it as just spin direction misses a lot of the weirdness. Prograde versus retrograde reality. When we say a planet rotates retrograde, we're making a statement that sounds simple but is actually a statement about a reference frame. Rotation direction, like most things in physics, only means something relative to something else. If you're floating alone in empty space and you spin, there's no way to say whether you're spinning clockwise or counterclockwise, because there's nothing to compare against. Direction requires context. In the solar system, the context we've agreed on is the orbital plane, the flat pancake where most of the action happens. If you look at the solar system from above the sun's north pole, looking down, everything orbits counterclockwise. That's the convention. Anything that rotates counterclockwise from this viewpoint is prograde. Anything that rotates the opposite direction is retrograde. Venus, viewed from this standard angle, rotates clockwise, opposite to everything else, backward relative to its own orbit. Its axis of rotation is almost anti-parallel to the solar system's angular momentum axis, which is another way of saying the same thing. The planet is, by any standard description, inverted. Now here's where it gets subtle, because there are actually two ways to describe what we observe. You can describe Venus as a planet whose rotation direction has been reversed relative to its formation, or you can describe Venus as a planet that has been flipped nearly upside down while retaining its original rotational sense. Geometrically, these are indistinguishable. If I take a spinning top turning counterclockwise and I pick it up and turn it upside down, from my perspective, it's now spinning clockwise, but the top itself, in its own frame, is still doing the exact same rotation. The top hasn't slowed down or reversed, I've just changed my vantage point on it. Venus looks retrograde from our vantage point. Is that because Venus actually reversed its rotation, or because Venus got tipped over? This matters for the physics of how it happened, because these two options imply very different sequences of events. A true rotational reversal would require mechanisms that directly act on the planet's rotation rate, driving it from positive through 0 to negative over some timescale. That's what the tidal models describe. An axial flip, on the other hand, would require the planet's rotation axis to be reoriented in space, probably through some interaction with another large body, or through some complex combination of torques acting on a non-rigid body. The planet's rotation itself wouldn't necessarily change much in its own frame, but its orientation relative to the rest of the solar system would. One is a slowing and reversing story. The other is a tipping over story. Both give you Venus's current observed state, but they describe fundamentally different histories. Most serious models of Venus don't treat these as cleanly separable, because, in reality, the tidal and gravitational torques that act on a spinning planet over billions of years can affect both the rotation rate and the orientation of the axis, coupled together. The Correa and Lascar models, which we'll get to in detail, actually suggest that the evolution can proceed along either path and the final state can be the same either way, which is, again, the degeneracy problem. Multiple histories collapse into the same present, and we can't distinguish between them without more data than we currently have. For now, it's enough to say that Venus is unusually oriented and unusually rotating, in a way that cannot be accounted for by any of the standard formation processes, and that requires a specific explanation beyond the default inheritance from the disk. Mercury, for comparison, has been spin-evolved by tidal interactions with the Sun, but it's settled into a 3-to-2 spin-orbit resonance that's easily explained by standard tidal physics. Earth has been slowed somewhat by its moon, which is a well-understood process. Mars spins at nearly the same rate as Earth, despite being much smaller, because nothing significant has happened to its rotation in a long time. None of these other inner planets presents the kind of anomaly Venus presents. And Uranus, which people sometimes bring up as another retrograde-ish world, is a different kind of weird. Uranus is tipped at about 98 degrees, which means its rotation axis lies nearly in the plane of its orbit. It's rolling on its side through the solar system. The leading explanation for Uranus is a massive early impact, possibly with an Earth-sized body that knocked it over. Uranus is not a great analogue for Venus, because Uranus is tipped, not fully inverted, and because Uranus has moons and a ring system that help anchor our models of what happened to it. Venus has neither. Uranus's moons orbit in the equatorial plane of the planet, which means they're also tipped over, which strongly suggests the impact happened before or during the formation of the moon system. The moons are a historical record. Venus has no equivalent record, so the inversion of Venus remains uniquely unexplained. And it gets more unexplained the more you think about how slowly it's rotating, which brings us to the numbers, which are genuinely strange in a way that doesn't get emphasized enough. The scale problem nobody feels. Imagine standing on Earth's equator right now. You are moving, at this moment, at about 1,040 miles per hour, or 1,670 kilometers per hour. That's the speed at which the surface of Earth is carrying you around our planet's rotation axis. You don't feel it because everything around you is moving with you, but the speed is real. At that velocity, if you weren't moving with the Earth would be a blur zipping past you like a train. Now stand on Venus's equator, hypothetically, in your imagination. How fast is the surface moving under you? About 4 miles per hour, or 6.5 kilometers per hour. That's walking speed. That's a brisk stroll. You could jog and keep up with the rotation. You could probably keep up with it by just walking at a reasonable pace. Let that sink in. A planet roughly the size of Earth, with roughly the same mass, is rotating so slowly that a human in good shape could, in principle, outrun its equatorial rotation. The planet is barely moving. It's less like a spinning world and more like a slowly turning lathe. And this has profound implications for what kinds of physics become important on that planet's long-term evolution. The 243-day sidereal rotation period is the time it takes Venus to rotate once relative to the distant stars. But from the perspective of someone standing on Venus looking at the Sun, the solar day is different, because Venus is also moving around the Sun while it's rotating. The solar day on Venus is about 116.75 Earth days. That's still extraordinarily long, but it's shorter than the sidereal day because the retrograde rotation actually combines with the prograde orbital motion in a particular way. If you did the math carefully, you'd find that the Sun rises and sets on Venus, but only twice per Venusian year. A single day-night cycle on Venus, from sunrise to sunrise, takes 117 Earth days. You'd experience 2 sunrises per year. That is, again, not how days and years work in any system we're intuitively familiar with. Slow rotation changes the physics of a planet in ways that fast rotation doesn't. On Earth, our rotation is fast enough that Coriolis effects are strong, weather patterns get sheared, the atmosphere has well-defined circulation cells, and day-night temperature contrasts are moderate because the surface only has 12 hours to heat or cool before the cycle switches. On Venus, the rotation is so slow that the Coriolis force is weak, which lets the atmosphere develop a very different circulation pattern. The day-night temperature contrast on Venus, however, is not dramatic because the atmosphere is so thick and so efficient at distributing heat that both hemispheres are roughly the same temperature. But the slow rotation means that small torques acting on the planet for long periods can accumulate into meaningful rotation changes, which is not true for fast rotators. This is the key insight that sets up the slow physics hypothesis. When a planet is spinning fast, tiny torques are basically irrelevant. You can exert a small torque on a rapidly rotating body for billions of years and barely change anything. But if the planet is already slow, those same tiny torques become dominant. The system becomes sensitive to influences that would be negligible on a fast rotator. Venus's slow rotation may not be just a consequence of something happening to it. It may also be a condition that allowed the unusual physics to take over and reshape the rotation further. It's a feedback loop. Slow rotation lets weird physics happen. Weird physics makes the rotation even weirder. So Venus isn't just spinning backwards. Venus is spinning backwards and slowly, and the combination is what makes it so strange. because both features point toward a history involving long-duration, low-intensity torques, possibly combined with earlier catastrophic events. And that brings us to the atmosphere, which turns out to be one of the largest players in this whole story, even though it's invisible to anyone who isn't looking carefully. The hidden clue: atmosphere coupling. Venus has an atmosphere about 93 times more massive than Earth's atmosphere. 93 times. Imagine piling 93 Earth atmospheres on top of your head. The pressure at the surface of Venus is about 92 times Earth's surface pressure, which is equivalent to the pressure you'd experience about 900 meters under the ocean on Earth. If you were standing on Venus, the atmosphere alone would crush you before you could notice anything else about the environment. That's assuming you hadn't already been cooked by the 465 degrees Celsius surface temperature, which is hot enough to melt lead. The atmosphere is mostly carbon dioxide, about 96.5%. The rest is mostly nitrogen, with traces of sulfur dioxide, water vapor, carbon monoxide, argon, and other gases. The clouds are sulfuric acid droplets, not water vapor. The greenhouse effect is so intense it makes Venus the hottest planet in the solar system, hotter even than Mercury, which is much closer to the Sun. But the most bizarre thing about the Venusian atmosphere, for our purposes, is that it rotates on its own, not with the planet, faster than the planet, much faster. The upper atmosphere of Venus, specifically the cloud layer around 65 kilometers altitude, races around the planet in about 4 Earth days. The planet itself takes 243 days to rotate once. The atmosphere is moving roughly 60 times faster than the surface. This is called superrotation, and it is one of the most enduring mysteries in planetary atmospheric science. Superrotation was first identified in the 1960s through tracking cloud features in ultraviolet images, and it's been confirmed and refined by subsequent missions. Most recently, the Japanese Akatsuki spacecraft, which arrived at Venus in 2015 and began detailed atmospheric mapping. The winds at cloud level blow at speeds of about 100 meters per second, or around 360 kilometers per hour, while the surface underneath them is moving at a pedestrian pace. The atmosphere and the solid body of the planet are almost decoupled rotationally. They're doing completely different things. And this is where it gets interesting from a spin physics perspective, because the atmosphere contains a real, significant amount of angular momentum. 93 Earth atmospheres of mass moving fast relative to the planet's surface represents a reservoir of rotational energy and momentum that cannot be ignored. The planet and the atmosphere are coupled. They exchange momentum through friction at the surface and through what are called thermal tides, which are bulges in the atmospheric density caused by solar heating that get dragged around the planet as it rotates. These thermal tides exert a torque on the solid planet. The key insight which has emerged over the past few decades is that Venus's rotation cannot be correctly modeled by treating the planet as a rigid body alone. You have to model it as a coupled system, with the solid planet on one hand and the massive atmosphere on the other hand, exchanging angular momentum through various mechanisms and both responding to external forces like solar gravitational tides and solar thermal input. When you do this, you find that the atmosphere can exert a significant influence on the rotation of the solid planet over long timescales. The thermal tides, in particular, can exert torques that push the planet's rotation in directions it wouldn't go on its own. This is the crack in the story that lets the slow physics hypothesis get started. If the atmosphere can push the planet's rotation around, then maybe Venus's strange spin isn't entirely about catastrophic events in its past. Maybe some of it is about ongoing coupling with a thick, hot, constantly stirred atmosphere that has been working on the planet for billions of years, and whose cumulative effect, integrated over cosmic time, has been significant. We'll explore this in much more detail in a later section, but for now, hold on to this fact. The atmosphere of Venus is not just a passive blanket of gas sitting on top of a spinning rock. It's an active participant in the rotational evolution of the planet. It's part of the system, and any theory of Venus's spin that ignores the atmosphere is, at best, incomplete. This coupling is also why Venus's spin is so difficult to reconstruct historically. The atmospheric torques depend on the density, composition, and temperature of the atmosphere, all of which have changed over billions of years. Early Venus might have had a very different atmosphere, maybe even liquid water oceans. If the atmospheric coupling strength has changed dramatically over time, then the effective torque on the planet's rotation has changed too, and the history of Venus's spin becomes contingent on the history of Venus's atmosphere, which we also don't fully understand. Every piece of the puzzle depends on every other piece. Which brings us to the question that started the whole field 60 years ago. What could have reversed Venus's rotation? And the oldest, simplest answer, the one that people reached for first, was impact. Something hit Venus. Something big. Something strong enough to flip a planet. The original idea, right after the radar discovery, when the planetary science community was still processing the fact that Venus was rotating backwards, the first reflex hypothesis was collision, and you can understand why. It's the most intuitive explanation for a dramatic anomaly. The planet is behaving strangely. Something must have done this to it. A giant asteroid, or a wayward protoplanet slammed into Venus at some point in its history, transferred a lot of angular momentum, and either stopped its rotation, reversed it, or tipped it completely over. Case closed, or so it seemed. The impact hypothesis has a long pedigree in planetary science, for good reasons. We know impacts happen. We have direct evidence of them throughout the solar system. The Moon's face is a crater-pocked record of billions of years of impacts. Mercury is similarly battered. Mars has enormous impact basins. Earth had its own planet-scale impact that produced the Moon. The early solar system was a violent place, and large bodies crashing into each other was a regular occurrence during the first few 100 million years. So proposing that Venus experienced a spin-altering impact isn't proposing something exotic. It's proposing something that, in principle, happened to every terrestrial planet in some form or another. The early 1965 papers on Venus's rotation did float the impact idea, at least in general terms. The specific mechanism would be a glancing blow from a large body, big enough to deliver substantial angular momentum in the opposite direction from Venus's rotation, but not so big that it completely destroyed the planet. You can imagine it like a cosmic cue ball striking Venus in just the right way to flip its spin while leaving the planet structurally intact. The math is straightforward in principle. You calculate the angular momentum Venus has now, you compare it to what Venus probably had originally, similar to Earth, more or less, and you figure out how much angular momentum had to be added in the opposite direction. Then you figure out what size impactor, hitting at what angle and what speed, could have delivered that much. When you run those numbers, you get an impactor that's roughly Mars-sized or larger, something on the order of a few thousand kilometers across, hitting Venus obliquely at a significant fraction of orbital velocity. This is a very big impact. Not as big as the one that formed Earth's moon, but in the same general ballpark, an event that, if it happened, would have been one of the defining moments in the solar system's history. And this is, in a sense, what makes it appealing. The drama of the event matches the drama of the anomaly. You want a big answer for a big question, and an impact that flipped a planet is a satisfyingly big answer. It's the kind of explanation that would make a great scene in a documentary. Molten rock flying into space, a planet wobbling under the force of the collision, everything changing in an instant. From the perspective of scientific storytelling, it's almost perfect. The problem, as always, is that scientific storytelling has to be backed up by scientific details, and the details on the impact hypothesis started getting uncomfortable almost as soon as people began looking closely. Which brings us to why this elegant, intuitive explanation turned out to be more complicated than it first appeared, and why the community mostly moved away from it, at least in its original form, over the decades that followed. Why it breaks physics. Here's the fundamental problem with a late-stage impact reversing Venus's spin. The energy involved in an event like that is catastrophically large, and it would have done a lot more than just change the rotation. It would have reshaped the entire planet. And we don't see evidence of that kind of reshaping. An impactor capable of reversing Venus's rotation would have to be, as we established, at least Mars-sized. When an object that big hits a planet, the kinetic energy released is enormous, on the order of 10 to the power of 32 joules or more. That's enough energy to melt a substantial fraction of Venus's mantle. It's enough to eject a huge amount of crustal material into space. It's enough to vaporize oceans, if there were any, and blow off most of the atmosphere. It's enough to form a debris disk around Venus that would, over time, accrete into one or more moons. Venus has no moons. None. Zero. This is one of the most underappreciated facts about our sister planet. Earth has one moon. Mars has two, both small. Even Mercury, tiny Mercury, has a record of impacts that we can read in its cratered surface. Venus has no orbiting companions at all. If a giant impact flipped Venus's rotation, where's the debris? Where's the captured fragment? Where's the secondary body that should, by all rights, have formed from the ejector? The absence of moons is hard to reconcile with a Mars-sized impact scenario. Furthermore, the surface of Venus, at least the surface we can see now, doesn't show evidence of a global-scale impact. The surface is, to be fair, young. It's been resurfaced by volcanic activity over the past 500 million years or so, which means whatever original impact scars might have existed have been covered over. So you could argue that the evidence has been erased, but this cuts both ways. If we can't see evidence of the impact, we also can't confirm that it happened. We're reasoning from absence, and absence is a weak form of evidence in either direction. The timing is another issue. If the impact happened early, during the accretion phase when Venus was still forming, then the planet was still molten and malleable enough that a big impact might not leave obvious permanent features. Earth's moon-forming impact, which happened during this early phase, didn't destroy Earth because Earth was still partly molten and could re-equilibrate. But an early impact has its own problems. During the accretion phase, Venus hadn't fully finished forming yet, and the planet's final rotational state would be determined by all the subsequent accretion that happened after the impact. The last bits of material Venus swept up would tend to spin it back in the prograde direction, matching the overall rotation of the disk. You can try to save the impact hypothesis by making it later, after Venus had finished forming. But then you run into the debris problem again, plus the fact that the energy deposited would have been enough to leave much more obvious signatures than we see, unless the signatures have all been covered up by later volcanic resurfacing. But if you have to invoke comprehensive evidence destruction to save your hypothesis, you're stretching pretty far. Over the 1970s and 80s, as planetary scientists developed more sophisticated simulations of planetary formation and impact physics, the simple late impact hypothesis for Venus became harder and harder to sustain. The energy budget didn't work. The angular momentum budget didn't work cleanly. The lack of moons was awkward. The lack of surface evidence was awkward. The community didn't abandon the idea entirely, because nothing better had fully taken its place. But the enthusiasm definitely waned. People started looking for alternatives. People started thinking about slower, more subtle mechanisms. People started wondering if the answer wasn't a single dramatic event, but a long, quiet accumulation of many smaller effects. And that's when, around the turn of the millennium, a new variant of the impact idea emerged that addressed some of the original problems by shifting the timing and opened a different can of worms about how the early inner solar system actually worked. The 2008 revival. In about 2008, a new set of simulations and hypotheses began appearing in the literature that revived the impact-based explanation for Venus's rotation, but with an important twist. Instead of a single giant impactor slamming into an already formed Venus, the new scenario suggested that Venus might have formed through the merger of two large protoplanetary bodies, each roughly Mars-sized, during the early accretion phase. And the geometry of that merger could have set Venus's unusual rotation from the start. This is a subtle but important shift. The original impact hypothesis had an asteroid or protoplanet striking a fully formed, roughly Earth-sized Venus and changing its pre-existing spin. The new merger hypothesis has two proto-Venuses colliding and sticking together to become the Venus we see today, with the combined object inheriting whatever rotation the collision geometry dictated. If the two bodies were approaching each other in a way that produced a net retrograde angular momentum when they merged, the resulting planet would naturally end up rotating backwards. No need to undo a pre-existing prograde spin. The spin was set at the moment of merger. The advantage of this scenario is that it happens during a time in solar system history when big collisions were, in fact, common. The protoplanetary disk was a chaotic place. Many objects the size of Mars or larger were wandering around, interacting, colliding, merging. The formation of terrestrial planets was not a smooth, orderly process. It was a series of collisions. The moon-forming impact on Earth is one well-documented example, but there were many others, some of which have left traces and some of which have not. A merger origin for Venus's rotation fits naturally into this chaotic formation framework. It doesn't require a special, unlikely event late in the planet's history. It requires a reasonably probable event during a time when such events were normal. The N-body simulations that support this kind of scenario show that, out of many possible formation pathways, a small but non-zero fraction produce planets with retrograde rotation through exactly this kind of merger geometry. The probability is low, maybe a few percent, but not negligible. And since we're only trying to explain one planet in our solar system, not all of them, a low probability event is actually acceptable. Rare things happen. We just happen to live in the solar system where the rare thing happened to Venus. The merger hypothesis also handles the moon problem better than the late impact hypothesis. Early in accretion, debris from collisions is often reaccreted by the growing planet, rather than settling into long-term orbit, because the planet is still absorbing material. So a merger-formed Venus wouldn't necessarily leave behind a moon-forming debris disk. The moon of Earth formed because the impact happened late enough and in just the right way that a stable disk could form. If Venus's defining collision happened earlier, or in a different geometry, no stable moon system would develop, and we'd see exactly what we see today, a moonless planet. There are still problems with the merger hypothesis, of course. You need two large protoplanets in the right place at the right time, approaching each other in just the right geometry. You need them to stick together rather than bouncing apart. You need the resulting planet to settle into its current orbit and not get disrupted by further collisions. Each of these requirements is plausible on its own, but chaining them together reduces the overall probability. And the hypothesis is not directly testable, because whatever moment of merger happened 4.5 billion years ago, and all the evidence is buried under billions of years of subsequent evolution. Still, the merger hypothesis is a respectable contender. It's consistent with what we know about how terrestrial planets form. It doesn't require any special physics. It can account for Venus's rotation without invoking a miraculous late-stage impact or an unusual capture event. And it leaves room for the atmospheric evolution of Venus to be shaped by subsequent events, including significant water loss, which is the next piece of evidence we need to talk about, because it might be another fingerprint of whatever happened to Venus in its deep past. Water loss connection. One of the most interesting clues about Venus's history doesn't come from its rotation or its surface or its atmosphere's bulk composition. It comes from hydrogen isotopes. Specifically, the ratio of deuterium to hydrogen, or D/H, in Venus's atmosphere. Regular hydrogen has 1 proton and no neutrons. Deuterium is a heavier isotope of hydrogen with 1 proton and 1 neutron, roughly twice the mass. Both behave chemically like hydrogen, but the heavier isotope is less likely to escape a planet's gravity. When a planet loses hydrogen to space, usually through atmospheric stripping driven by solar radiation or other escape processes, the lighter regular hydrogen escapes preferentially. The heavier deuterium is more likely to be left behind. Over time, this enriches the remaining atmosphere in deuterium relative to hydrogen. Earth's atmosphere has a D/H ratio of about 1.5 times 10 to the negative 4th. That's roughly the average value for the inner solar system, and consistent with what you'd get from water delivered during formation. Venus's atmosphere has a D/H ratio about 150 times higher than Earth's. That's an enormous enrichment. It's the kind of enrichment that happens when a planet has lost an enormous amount of hydrogen to space over billions of years. Why does this matter? Because the most natural source of atmospheric hydrogen on a planet like Venus is water. Water, chemical formula H2O, is made of 2 hydrogens and 1 oxygen. When water is broken apart by solar radiation in the upper atmosphere, the hydrogen can escape to space while the oxygen remains. Over time, a planet that started with a lot of water can lose essentially all of it through this process, leaving behind oxygen that gets bound up in rocks or atmospheric chemistry. The high D/H ratio in Venus's atmosphere suggests that Venus once had substantial water, and that most of it has been lost. How much water? Estimates vary, but some calculations suggest that Venus could have had enough water in its early history to cover the surface to a depth of several hundred meters, comparable to the ocean volume of Earth. That's a lot of water. That's enough to potentially have supported a habitable environment early in Venus's history, before something went wrong and the planet turned into the hellscape we see now. This is the Venus habitability question, which has been getting more attention recently. Was Venus ever Earth-like? Did it have oceans? Did it have a temperate climate? For how long? And what happened to change it? The connection to Venus's rotation is subtle, but potentially important. One hypothesis for how Venus lost its water involves a runaway greenhouse effect that started when the sun got hot enough to evaporate the oceans. Once water vapor is in the atmosphere, it's a greenhouse gas that warms the planet further, evaporating more water and so on until the oceans are gone. But this process depends on the planet's climate dynamics, which depend on its rotation, which depend on its atmospheric coupling, which depend on the history we're trying to reconstruct. If Venus's unusual rotation is a result of an early catastrophic event, and that event also stripped off a substantial portion of the original atmosphere and water, then the spin history and the water history are connected. The same catastrophe that flipped the planet might have also blown off the oceans. Alternatively, if Venus's rotation evolved gradually over billions of years through slow physics, then its water loss might have been a separate, slower process driven by solar heating alone. The two scenarios predict different isotope signatures and different amounts of remaining water. Upcoming missions, particularly NASA's Da Vinci mission, are specifically designed to measure these isotope ratios with unprecedented precision by sampling the Venusian atmosphere directly as the probe descends through it. If the D/H ratio turns out to be consistent with gradual loss over billions of years, that favors the slow physics picture. If the ratios show signatures of rapid early loss, that favors the catastrophic event picture. These are not clean distinctions, but they can narrow the space of possibilities. The isotope fingerprint is one of the few remaining pieces of direct evidence we have from Venus's early history, because the geological record has been wiped. It's a chemical fossil embedded in the atmosphere, telling us something about what Venus used to be. Whatever the specific story of Venus's rotation turns out to be, it is almost certainly connected to the story of Venus's water, and both are connected to the story of the early solar system. You can't tell any one of these stories without the others. So, we have two general families of catastrophic explanations: the late impact hypothesis, which doesn't work very well, and the early merger hypothesis, which works better but still has gaps. Both of these put Venus's weird spin down to a specific event in the planet's past, but there's a completely different family of explanations that says the opposite. That says you don't need any catastrophe at all. That says Venus's spin can be explained by the slow accumulation of tiny forces over billions of years. And this second family of explanations has been gaining ground among planetary dynamicists for the past few decades, to the point where it's now arguably the leading framework for understanding the Venus rotation problem. Let's talk about it. The Correa-Lascar model. In the early 2000s, two planetary dynamicists, named Alexandre Correa and Jacques Lascar, began publishing a series of papers that laid out a new framework for understanding Venus's rotational state. Their argument, roughly, was that Venus's current spin could be the natural outcome of billions of years of slow evolution, driven by a small number of continuously acting torques, without requiring any giant impact or merger. The framework has become known informally as the Correa-Lascar model, and it represents a fundamentally different way of thinking about the problem. The idea is this: a planet's rotational state is not just a function of its initial conditions, it's also a function of all the forces acting on it over time. If those forces are continuously operating, then the planet's rotation will evolve towards some equilibrium or attractor state determined by the forces themselves, rather than by the initial conditions. If you start with a planet spinning prograde, and you let it evolve under a specific set of torques for billions of years, it might end up in a retrograde state, or a slowly spinning state, or some combination of both, depending on the physics. The initial condition becomes less and less relevant as time goes on. For Venus, the Correa and Lascar models identify three main torques that act on the rotation. The first is the solar gravitational tide. The Sun's gravity pulls slightly harder on the near side of Venus than the far side, which deforms the planet into a slight ellipsoid shape with bulges on both sides. Because Venus is rotating, even slowly, and because there's a delay in how the planet responds to the tidal stress, the bulges don't line up perfectly with the Sun. They're slightly offset. This offset produces a torque that slows the rotation down. This is the same basic physics that causes Earth's rotation to be slowing down very gradually due to tides raised by the Moon and the Sun, and it's what caused Mercury to settle into its spin-orbit resonance. The second torque is the atmospheric thermal tide. This is the one that's more unique to Venus. The Sun heats the day side of the planet, which causes the atmosphere on the day side to expand and become less dense. The night side is cooler and denser. This creates a density asymmetry in the atmosphere, with a bulge on the day side and a depression on the night side. Because the atmosphere is dragged along with the planet's rotation, sort of, but also responds to the heating pattern, the actual density distribution ends up offset from the simple day-night gradient. This offset distribution has a gravitational effect on the solid planet beneath it, and through that gravitational effect exerts a torque. The key fact is that the thermal tide torque acts in the opposite direction from the gravitational tide torque. While the gravitational tide tends to slow the rotation down towards zero, or toward a prograde synchronous state, The thermal tide tends to push the rotation in the retrograde direction. The third torque is core mantle friction. Venus has a liquid metal core surrounded by a solid rocky mantle. These two layers can rotate at slightly different rates, and the friction between them at the core mantle boundary transfers angular momentum between them. This is a smaller effect than the tides, but it's not negligible over billions of years, and it can affect how quickly the rotation responds to the other torques. These three torques interact with each other in complicated ways. The strength of the gravitational tide depends on the rotation rate, the internal structure of the planet, and the distance from the Sun. The strength of the thermal tide depends on the atmospheric density, the composition, and the heating pattern. The core mantle friction depends on the interior structure and the rotation rate. As the rotation changes, all three torques change, and the system evolves in a way that's not easy to predict without detailed numerical simulation. Correa and Lascar ran those simulations, starting Venus from a wide range of initial rotational states and letting the coupled system evolve over billions of years. What they found was that the system is sensitive to initial conditions in a specific way. There are multiple possible end states, called attractors, that the rotation can settle into. Some of those attractors correspond to prograde rotation, some to retrograde, some to very slow rotation close to zero. Depending on the initial conditions and the specific strength of the various torques, Venus could end up in any of these states. Importantly, the current state of Venus' slow retrograde rotation, with nearly 180-degree tilt, is consistent with one or more of these attractors. In other words, the Correa-Lascar framework says that you can get the current Venus without any catastrophic event. You just need the right initial conditions, which might not even be particularly special, and billions of years of quiet evolution under the standard set of torques. Venus is where it is because the dynamics naturally led it there, not because something exotic happened. This is a very different kind of explanation from the impact or merger hypotheses. It doesn't require a specific event. It doesn't require a specific time. It doesn't require any particular initial condition beyond something in the right general range. It's more of a statistical explanation, saying that under the physics we understand, Venus's current state is one of several possible outcomes, and we just happen to live in the version of the solar system where it ended up at this particular attractor. The three invisible torques. Let me walk you through those three torques in a little more detail, because the way they interact is really the heart of why Venus is so unusual, and because it's worth understanding why the atmosphere is so central to this whole picture. The gravitational tide from the Sun is probably the most familiar of the three. Here's how it works. Gravity gets weaker with distance. The Sun's gravity is stronger on the side of Venus facing the Sun than on the side facing away. This differential gravity pulls on the two sides of the planet unequally, stretching the planet slightly along the Sun-Venus line. You get a small bulge pointing toward the Sun, and another small bulge pointing away from the Sun. This is the same physics that causes ocean tides on Earth, except on Venus, the solid planet itself deforms because there are no oceans. If Venus were not rotating, the bulges would line up exactly with the Sun. But because Venus is rotating, and because the material of the planet takes time to deform and relax, the bulges are slightly dragged around by the rotation. They end up offset from the Sun-Venus line. The near side bulge is slightly ahead of the Sun in the direction of rotation, and the far side bulge is slightly behind. This offset creates a torque on the planet because the Sun's gravity is still pulling on those bulges, and the misalignment means the net pull has a rotational component. The direction of that torque depends on the direction of rotation. If Venus is rotating prograde, the gravitational tide exerts a torque that opposes the rotation, slowing the planet down. If Venus is rotating retrograde, the torque still opposes the rotation, which now means it's pushing in the prograde direction. Either way, the gravitational tide acts to drive the rotation towards zero. Over long enough time, it would tend to lock Venus into a synchronous rotation with the Sun, meaning one face permanently pointed at the Sun, like the Moon to Earth. Now consider the thermal tide in the atmosphere. The Sun heats the day side of Venus. The heated gas expands upward, creating a low-pressure region at the surface and a high-pressure region at altitude on the day side. On the night side, the opposite happens. This sets up a pressure gradient that drives winds, which, over time, redistribute the heat. But the response is not instantaneous. There's a lag, and because of that lag, combined with the rotation of the atmosphere, the actual thermal structure of the atmosphere is not symmetric about the Sun-Venus line. There's a rotating pattern of density highs and lows. The gravitational pull of this density pattern on the solid planet beneath it exerts a torque, just like the gravitational tide does. But crucially, the direction of this torque is opposite to the direction of the gravitational tide torque. Where the gravitational tide pulls the rotation towards zero, the thermal tide pushes the rotation away from synchronous in the retrograde direction. These two torques fight each other. The balance between them depends on a lot of factors. The mass of the atmosphere matters. Venus has a very thick atmosphere, which makes the thermal tide unusually strong. The rotation rate matters. When the rotation is very slow, both tides are weak. When the rotation is faster, the tides are stronger and the balance between them can shift. The distance from the Sun matters. Venus is close enough to the Sun that both tides are significant. In principle, the two torques can balance each other, and when they do, the rotation can stabilize at a specific non-synchronous value, or the thermal tide can dominate and drive the rotation into retrograde. The third torque, core mantle friction, is more subtle. Venus has a differentiated interior with a dense iron core in the center, surrounded by a rocky mantle. The core is partially or fully liquid, and it can rotate at a slightly different rate than the mantle. When the rotation rate of the outer layers changes due to tidal torques, for instance, the core doesn't immediately follow. There's friction at the core mantle boundary that slowly transfers angular momentum between the two. This friction acts as a kind of damping on the rotation evolution, and it can affect how quickly the system responds to the tides. When you put these three torques together and let them evolve over billions of years, the dynamics are complex. The rotation state is not a fixed point, but an attractor in a high-dimensional phase space, and the phase space has multiple attractors. Which attractor Venus ends up in depends on its initial conditions, the specific values of the various physical parameters, and small perturbations along the way. The simulations suggest that the current state of Venus' 243-day retrograde rotation with high tilt is one of the possible attractor states, reachable from a range of plausible initial conditions. The atmosphere is the key. Without the massive, super-rotating, thermally active atmosphere of Venus, the thermal tide torque would be negligible, and the rotation would just slowly decay to synchronous under the gravitational tide. The atmosphere is what makes Venus special. The atmosphere is what allows the rotation to stabilize at a non-synchronous value, or to be driven into retrograde, or to end up tilted at a bizarre angle. The atmosphere is, in a very real sense, the engine that rewrites Venus's rotation. And this, circling back to our central thread, means Venus's spin isn't just a property of the solid planet, it's a property of the coupled planet-atmosphere system. You cannot understand Venus's rotation without understanding its atmosphere, and you cannot understand its atmosphere without understanding its rotation. The two are deeply entangled, and both have been evolving together for billions of years. Two possible end states. One of the more unsettling results from the Correa-Lascar analysis is that within their framework, there are actually multiple ways Venus could have ended up in its current state, and those different pathways all look identical from the outside. The first pathway is what you might call gradual reversal. Venus starts out rotating prograde at some reasonable speed, similar to early Earth. Over billions of years, the combination of gravitational and thermal tides slows the rotation down. At some point, the rotation passes through zero and begins to go retrograde. The thermal tide, which is now acting in the direction of rotation because the rotation is retrograde, continues to speed up the retrograde rotation until it reaches a balance with the gravitational tide at the current 243-day period. Throughout this process, the axial tilt remains small. The planet was always right side up, more or less. It just changed direction. The second pathway is what you might call axial flip. Venus starts out rotating prograde, as before. But instead of slowing to zero and reversing, the planet's rotation axis gets destabilized by the torques. The axis migrates away from its original orientation and tilts over. Eventually, it tilts past 90 degrees and keeps going, until it reaches the current tilt of nearly 180 degrees. At this point, the planet is effectively upside down. Its rotation direction in its own frame might not have changed much, but from our external perspective, it now looks retrograde. The planet tipped over, and its apparent rotation reversed as a result. The present-day appearance of Venus is consistent with either pathway. In both cases, you end up with a planet that looks, from the outside, like it's rotating backwards very slowly with an extreme axial tilt. In both cases, the observed dynamics are the same. The internal structure of the planet, the composition of its atmosphere, and the overall mass distribution would all be essentially indistinguishable between the two histories. This is called observational degeneracy. Multiple histories collapse into the same present. Unless you have extra information, you cannot work backward from the current state to determine which history actually happened. And for Venus, we don't have the extra information. We don't have a preserved early magnetic field that might have recorded the rotation axis orientation at different times. We don't have preserved ancient crust that might show characteristic features of one history or the other. We don't have satellites whose orbits might have been frozen in during an earlier phase. We have the current state and nothing else. The Correa-Lascar simulations actually suggest that the axial flip pathway and the gradual reversal pathway have different probabilities depending on the exact parameter values you assume. Under some parameter choices, axial flip is more common. Under others, gradual reversal is more common. But both are possible, and both can be produced without any catastrophic event. The slow physics can take Venus to the current state through either route. When you combine this with the impact and merger hypotheses, the degeneracy problem becomes even worse. You now have at least 4 distinct possible histories for Venus's rotation: gradual slow reversal, gradual axial flip, early merger with retrograde geometry, and late catastrophic impact. All 4 can produce the current observed state. Distinguishing between them requires evidence that, so far, we don't have, and the evidence that could distinguish them has, in most cases, been erased by billions of years of volcanic resurfacing and atmospheric turnover. This is, in a sense, the deepest problem with studying Venus. Not just that we don't know what happened, but that the planet itself has been systematically destroying the evidence of what happened, and we're trying to reconstruct ancient history from a present that has been heavily reworked. The problem nobody can escape. Let's sit with this a little, because it matters. Venus has a resurfacing problem that makes it nearly unique among the terrestrial planets. On Earth, we have old rocks. The oldest zircon minerals ever dated are about 4.4 billion years old, nearly as old as the planet itself. Through geology, we can read a fairly continuous record of Earth's history, going back most of the way to its formation. Mars has preserved surface features from its first billion years, including crater basins and ancient riverbed deposits. The Moon has its heavily cratered highlands, which preserve the original impact history of the inner solar system. Mercury has its Caloris basin and its crater record, largely preserved because Mercury has no atmosphere to speak of and no significant volcanism in recent eons. Venus has none of this. The surface of Venus is young, probably less than 1 billion years old, possibly as young as 500 million. Virtually all of the surface features we see are volcanic in origin, either lava flows or deformation of existing volcanic terrain. There's some debate about whether the resurfacing happened all at once in a catastrophic event sometime in the last 600 million years, or whether it's been continuous. But the key point is that whatever surface Venus had before that resurfacing event is gone, buried, melted, erased. This is devastating for our ability to reconstruct Venus's history. On other planets, we can read rotation-dependent features in the geology. On Earth, for example, we see latitudinal banding in ancient climate records because Earth's rotation and tilt affect how solar energy is distributed. On Mars, we see features consistent with changing obliquity over time. Venus shows us almost nothing of this kind. The geological record that would normally help us reconstruct the rotation history is simply not available. Venus also has no moons. Earth has the Moon, which is a frozen record of the impact that formed it and whose orbit has been gradually evolving ever since, encoding information about Earth's rotation history. Mars has Phobos and Deimos, tiny moons that nonetheless preserve some dynamical information. Even the giant planets have moon systems that encode histories of their formation. Venus has 0 moons, nothing in orbit around it, no ancient record written in the orbital dynamics of a companion object. Venus also has no significant magnetic field today, and as far as we can tell, it doesn't have a strong record of ancient magnetic field in its crustal rocks either. Again, part of the reason is that the crust has been resurfaced. Whatever paleomagnetic record might have existed has been melted and rewritten. On Earth and on Mars, paleomagnetic data has been invaluable for reconstructing the orientation of the planet's rotation axis over time. Venus denies us this tool. What we're left with is essentially the present-day state of the planet, plus whatever chemical fingerprints are preserved in the atmosphere, isotope ratios of hydrogen, xenon, argon, and a few other species, plus the structure of the interior, as inferred from gravity and seismic measurements, of which we have very limited data. This is not enough to uniquely reconstruct Venus's rotational history. Multiple histories remain viable, and the evidence that could distinguish them is not accessible with current observations. This is why the Venus rotation problem has remained unresolved for 60 years. It's not because the scientists working on it aren't smart. It's because the evidence required to resolve it is missing, and in some cases has been actively destroyed by the planet itself. Venus has done a thorough job of forgetting its past, and we're trying to reconstruct that past with the crumbs that remain. So impact, merger, gradual tidal evolution, axial flip, all viable, all unresolvable with current data. But there are even stranger ideas in the literature, ideas that don't invoke just Venus itself, but reach out to the rest of the solar system and say that maybe Venus's spin is the fingerprint of something much larger, something that happened to the entire inner solar system during its chaotic youth. Let's get into those. A missing planet. The inner solar system today has 4 planets: Mercury, Venus, Earth, and Mars. But this configuration is not necessarily the original one. Modern simulations of planetary system evolution have consistently shown that the early solar system was probably more chaotic and more populated than it is today. It's entirely possible that one or more planets that formed early in the solar system's history are simply not here anymore. They got ejected, they fell into the sun, they collided with each other, they disappeared. The hypothesis of a lost inner planet, sometimes called Planet V or a similar designation, has been floated in various forms for decades. The general idea is that there was a 5th terrestrial planet, possibly in an orbit between Mars and the asteroid belt or in some other unstable region, and that this planet played a role in shaping the early evolution of the inner solar system before eventually being ejected or destroyed. The specific scenarios vary. In some models, Planet V interacted gravitationally with the other planets and caused orbital migration or perturbations that left lasting effects. In others, Planet V caused the late heavy bombardment of the inner solar system around 3.9 billion years ago, flinging asteroid belt material inward through its unstable dynamics before it was finally removed. If Planet V existed, it could have had effects on Venus's rotation, directly or indirectly. A close gravitational encounter between Venus and a rogue Mars-sized body could have torqued Venus's spin axis, tipping it over or reorienting it. Multiple encounters with different bodies during a chaotic phase could have scrambled Venus's rotation in ways that are hard to simulate with any certainty. The Planet V hypothesis is not strictly necessary to explain Venus's rotation, but it's one of the pieces that sometimes gets mentioned in discussions of how the early inner solar system might have disrupted the rotational inheritance of its planets. The evidence for Planet V is not direct. It's inferred from dynamical considerations. If you try to simulate the evolution of the inner solar system using only the 4 planets we see today, you don't always reproduce the current configuration cleanly. Some simulations suggest that an additional body, or several additional bodies, might have been needed to stabilize the system into its current state. But these arguments are indirect and model-dependent. For our purposes, the Planet 5 hypothesis is interesting, mostly because it illustrates how Venus's rotation might be connected to larger questions about the history. If planets that used to exist no longer do, then the rotational and orbital states of the surviving planets have been shaped by interactions with objects we can no longer see. Venus's weird spin could be a frozen record of encounters with a vanished neighbor. This isn't a strong hypothesis in the sense of having direct evidence behind it, but it's a framework for thinking about the problem that opens up possibilities beyond the standard "something hit Venus" or "slow tides did it" stories. Earth-Venus exchange. Another variant of the chaotic early solar system idea involves closer encounters between Earth and Venus themselves. In some models, the early orbits of Earth and Venus were less well defined than they are now, and the 2 planets had episodic close approaches to each other. During these close approaches, gravitational interactions could have exchanged angular momentum between them, possibly tilting Venus's rotation axis or altering the relative orbital properties of the 2. This hypothesis has the appealing feature of explaining why Earth and Venus are so similar in some ways: mass, size, composition, general location, but so different in others: rotation, atmosphere, habitability. Maybe the similarity comes from the fact that they formed from the same zone of the disk, and the differences come from the fact that their early interactions diverged. A close encounter between Earth and Venus might have delivered angular momentum to one and taken it from the other, leading to Earth retaining a fast prograde spin, while Venus ended up with its current strange rotation. The evidence for this kind of scenario is, again, indirect and model-dependent. We have no direct geological or chemical evidence that Earth and Venus interacted in a specific way. The hypothesis is a thought experiment, an attempt to explain multiple features of the inner solar system with a single mechanism. Simulations can produce outcomes consistent with close encounters, but they can also produce the observed outcomes without invoking any. The hypothesis remains a minority view, one of several ideas in circulation rather than a widely accepted explanation. The reason I'm including it here is that it illustrates, again, how the Venus rotation problem can't really be separated from the rest of the inner solar system's history. You can't fully understand what happened to Venus without thinking about what was happening to everything around it at the same time. And when you do think about it that way, you realize that there are many possible histories that could be consistent with the current state of the system, and narrowing them down requires evidence that's mostly not available. Capture from elsewhere. The most exotic of the chaotic formation hypotheses is that Venus didn't form where it currently orbits. Instead, Venus formed elsewhere in the solar system, possibly farther out, and was gravitationally captured into its current orbit later. This kind of scenario is extremely rare in practice. Capturing a planet into a new orbit requires a delicate balance of conditions that almost never occurs. You need the incoming object to have just the right velocity relative to the capture target, the right geometry, and some way to dissipate energy so that it doesn't just fly past on a hyperbolic trajectory. In most cases, an object that encounters a planetary system will either be ejected or absorbed, not captured. For moons, capture is plausible because moons are small relative to their host planets, and gas, drag, or tidal interactions can provide the energy dissipation needed. Triton, the retrograde moon of Neptune, is the most famous example of a probable captured object. For planets themselves, capture is much harder because you'd need another large body to absorb the excess energy, and the orbital dynamics are more complex. Still, the capture hypothesis for Venus has been floated occasionally. The attraction is that it would explain the retrograde rotation naturally. A captured planet would carry its own rotational history with it, independent of the disk that formed the local inner solar system. If Venus formed somewhere with different dynamics, then its rotation wouldn't have to match Earth's or Mercury's or Mars's. The problem is that Venus's composition matches what we'd expect from an inner solar system origin. The silicate and iron content is consistent with formation at approximately the current distance from the Sun, not with formation farther out. If Venus had formed in the outer solar system, we'd expect it to be enriched in volatile compounds like water and methane, which it is not, or at least not in a way consistent with an outer system origin. The composition argument is strong enough that most planetary scientists consider the capture hypothesis implausible, though it persists as a minority view because it has the appeal of simplicity for the spin problem. Why these ideas exist at all? These chaotic and exotic hypotheses persist, even when they have weak evidence, because the standard explanations have gaps. When the leading models for Venus's rotation all have problems, the community naturally explores stranger ideas. And the stranger ideas illuminate something important about the early solar system, which is that it was almost certainly a lot more chaotic than the current configuration would suggest. Modern simulations, particularly the Nice model and related frameworks like the Grand Tack hypothesis, have suggested that the early outer solar system underwent significant orbital migration. Jupiter, in particular, probably moved inward and then back outward early in solar system history, disturbing everything in its path and scattering objects throughout the inner system. This migration could have delivered significant numbers of planetesimals into the inner solar system, caused instabilities, and reshaped the orbits of the terrestrial planets. If this picture is correct, then the inner solar system was a much more violent place than we might naively assume. Collisions were common, orbital instabilities were common, large bodies wandered in and out of the inner system for millions of years. Planets formed, grew, merged, were disrupted, and reformed in some cases. The calm, orderly solar system we see today is the end state of a chaotic process, and the properties of the surviving planets reflect both their formation conditions and the chaos they survived. In this context, Venus's strange rotation makes more sense as a potential outcome. A planet that survives a chaotic early solar system might end up with rotational properties very different from its original formation state, depending on what it went through during that chaos. The rotation isn't necessarily a clean record of initial conditions. It's a noisy record of everything that happened along the way. Venus, with its erased geological record and its isolated current state, is a frustrating object precisely because we can't see most of what it went through. The larger point, connecting back to our central thread, is that Venus's spin cannot be understood in isolation. It's part of a larger system that was, at some point in its history, much more chaotic than it is now. And the chaos of the early solar system is itself a scientific frontier, where our models are still being developed and tested. Venus is a data point in that larger story, and our difficulty explaining Venus is partly a reflection of our incomplete understanding of the solar system's earliest evolution. Chaotic resonance capture. There's another angle on the slow physics idea that's worth mentioning, and it's a bit more exotic than the Correa-Lascar picture. It involves the concept of chaotic resonance capture in dynamical systems. In many dynamical systems, particularly those involving gravitational interactions between multiple bodies, there exist specific configurations called resonances, where the orbital or rotational frequencies of different components are related by simple integer ratios. Resonances can be stable or unstable, attractive or repulsive. A system that's evolving under the influence of various forces can drift into a resonance and get stuck there, even if the resonance wasn't part of its initial conditions. For Venus, the idea is that the combination of gravitational tide, thermal tide, core mantle coupling, and planetary perturbations creates a dynamical system with multiple possible resonant states. Some of these states correspond to prograde rotation, some to retrograde, some to various tilts and rotation rates. As Venus's rotation evolves over billions of years, the system drifts through phase space and eventually gets captured into one of these stable resonances. Which one depends on the details of the evolution, which depend on initial conditions, which depend on perturbations that were present during the early evolution. This framework suggests that Venus's current state is not unique, but one of several possible attractors, and that small differences in initial conditions or early perturbations could have led to Venus ending up in a very different state. It also suggests that the transition into the current state might have been chaotic, involving periods when the rotation was changing rapidly and unpredictably before settling into the present stable configuration. The chaotic resonance framework is related to the Correa-Lascar picture, but extends it by emphasizing the role of multiple competing attractors and the sensitivity to initial conditions. It's more speculative in some ways because it relies on detailed simulations that are hard to verify, but it's consistent with the general observation that Venus's state is hard to reconstruct uniquely from the current data. Early sun tidal locking. Another idea that comes up occasionally is that early Venus might have been tidally locked to the Sun, and that its current rotation is the result of a release or modification of that locked state. When the Sun was younger, it was larger, hotter, and more active than it is now. The tidal interaction between a young, expanded Sun and a nearby rocky planet could, in principle, have been strong enough to lock Venus into a one-to-one spin-orbit resonance, similar to how the Moon is locked to Earth. If Venus was initially tidally locked to the Sun, then later solar evolution, the Sun contracting to the main sequence, becoming less tidally dominant, and other changes could have destabilized the lock. The planet might have then entered a period of rotational reorganization, during which its spin state drifted and eventually settled into the current retrograde slow rotation. This scenario doesn't obviously explain the inversion, but it's one component in a larger story about how Venus's rotation evolved during the early solar system. The evidence for early tidal locking of Venus is not strong. The Sun's early evolution is imperfectly understood, and the conditions that would have led to tidal locking versus faster rotation depend on parameters that are not well constrained. It's a possibility, not a confirmed hypothesis. Disk instability birth. A more exotic idea is that Venus was born with its unusual rotation from the very beginning due to local anomalies in the protoplanetary disk. The standard picture of planet formation assumes that the disk was smoothly rotating and that planets inherited the general rotation direction. But real disks are not perfectly smooth. They have turbulence. they have local instabilities. They have regions where gas and dust can form counter-rotating eddies under certain conditions. If Venus formed in a region of the disk with a local counter-rotating eddy, it could have inherited that counter-rotation from the start without ever rotating prograde. This would eliminate the need to explain how Venus's rotation was reversed, because it would never have been prograde in the first place. It would have been retrograde from birth. The problem with this hypothesis is that local counter-rotating eddies in protoplanetary disks, while not impossible, are expected to be rare. The conditions that produce them don't typically persist for long enough to allow a full planet to form within them. Most simulations of disk dynamics don't produce planetary-scale retrograde formation as a common outcome. So, while the disk instability idea is theoretically possible, it requires an unusual combination of conditions that's hard to argue for confidently. The reason this idea is still discussed is that it represents one of the few scenarios where Venus's rotation could be explained without any post-formation reshaping. It would simplify the story significantly. The challenge is just that the conditions required are rare enough that invoking them feels ad hoc. The atmosphere problem that breaks all models. I want to come back to the atmosphere one more time, because there's a specific feature of Venus's atmospheric behavior that doesn't fit cleanly into any of the models we've discussed. The superrotation of the Venusian atmosphere, where the clouds rotate 60 times faster than the surface, is not fully explained even now. We can describe it, we can model it, we can predict some of its properties, but we don't have a complete, self-consistent theory that says why the atmosphere rotates so much faster than the planet it's sitting on. Various mechanisms have been proposed. One is that the atmosphere is spun up by a combination of solar heating patterns and upward angular momentum transport through waves. Specifically, atmospheric waves, called Kelvin waves and Rossby waves, which are large-scale oscillations that propagate through the atmosphere, can transport angular momentum between different altitudes. If these waves preferentially transport momentum upward, they could continuously inject angular momentum into the upper atmosphere, maintaining the superrotation against the friction that would otherwise slow it down. The Akatsuki mission has given us detailed data on the atmospheric circulation patterns and has helped refine these models, but it has also revealed features that weren't expected. For example, the Akatsuki data has shown evidence of large standing waves in the atmosphere that may be related to topographic features on the surface below. The interaction between the atmosphere and the surface is more complex than the simple superrotation picture suggests, and the momentum exchange between these two layers is still being worked out. Why does this matter for our central question? Because the atmosphere is one of the main drivers of Venus's rotational evolution, at least in the Correa-Lasker framework. If we don't fully understand the current state of the atmosphere, we also don't fully understand how it's exerting torques on the solid planet today, let alone how it was doing so over billions of years. The models that predict Venus's current rotation from slow physics evolution depend on assumptions about atmospheric behavior, and those assumptions are not all well verified. This is the deepest level of the problem. Not only do we have multiple possible histories for Venus, and not only have the signatures of those histories been erased by resurfacing, but our model of the current state of the planet is itself incomplete. The atmospheric dynamics that drive some of our leading explanations are not fully understood. The coupling between the atmosphere and the solid planet is complicated. The long-term evolution is sensitive to parameters we can't measure precisely. Every piece of the problem has uncertainties, and the uncertainties compound as we try to go back in time. Venus is, in a real and humbling way, a problem at the limits of what current planetary science can solve. It's not a simple case of not having figured it out yet. It's a case of not having the evidence to distinguish between multiple possible answers and not having a complete enough understanding of the current state to be confident in our extrapolations backward. To make progress, we need new data, better atmospheric measurements, direct sampling of the interior, detailed topography, gravity field mapping at high resolution, all of which are goals of the next generation of Venus missions. The evidence problem. Let's take stock of what we actually have and what we don't. To reconstruct Venus's rotational history, we'd ideally want several kinds of data. We'd want an ancient surface record that preserves features sensitive to rotation, things like latitudinal climate zones or wind-eroded features that might show how the rotation was oriented long ago. We'd want a moon or satellite whose orbit encodes the early rotation state of the planet. We'd want a preserved magnetic field record in ancient rocks that shows how the rotation axis was oriented through geologic time. We'd want atmospheric isotope measurements precise enough to distinguish between rapid early loss and gradual long-term loss of volatiles. We'd want detailed interior structure information to constrain the tidal response and the core mantle coupling. We have almost none of this. Venus's surface is young, resurfaced by volcanism probably within the last 500 million years. The original crust from the planet's early history, if it ever existed in a recognizable form, is gone. Whatever ancient features might have encoded rotation information have been overwritten by lava flows and tectonic deformation. Our best surface imaging from missions like Magellan in the 1990s gives us a detailed picture of a surface that's too young to preserve the evidence we need. Venus has no moons. None. A moon would have been an invaluable record of the planet's early history, because moons tend to preserve dynamical information that can be reconstructed even after billions of years of evolution. Earth's moon tells us a great deal about Earth's past. Mars's moons, tiny as they are, tell us something about Mars's history. Even Mercury, without moons of its own, preserves a crater record that gives us timing information. Venus has none of this. Its dynamical environment is a planet alone in orbit around the Sun, with no companions to anchor our reconstructions. Venus has no magnetic field today. The planet has a metallic core that's at least partially liquid, and under the right conditions it could generate a magnetic field through dynamo action. But something about Venus's interior dynamics, perhaps the lack of strong core mantle convection due to the absence of plate tectonics, or perhaps the specific thermal state of the core, means that it doesn't maintain a global magnetic field. Without a current field, and without ancient magnetized rocks preserved on the surface, we can't reconstruct how the magnetic field, and by extension the rotation axis, might have changed over time. The only robust early history information we have about Venus comes from the atmosphere, specifically from the isotopic composition of gases like hydrogen, helium, argon, neon, xenon, and others. These isotope ratios are set by a combination of the primordial mix in the early solar system and the subsequent history of atmospheric loss and modification. By measuring them precisely, we can constrain the history of atmospheric evolution, which in turn constrains the history of volatile loss, which in turn constrains the thermal and rotational history of the planet. But our current measurements of Venus's atmospheric isotopes are imprecise compared to what we'd need to really pin things down. Most of the data comes from early Venus missions in the 1970s and 80s, when instrument precision was limited by the technology of the era and by the difficulty of operating in Venus's hostile environment. Getting better measurements requires new missions with better instruments, which brings us to what's coming next. What Da Vinci will measure. NASA's Da Vinci mission, scheduled for launch later this decade with arrival at Venus in the early 2030s, is designed specifically to address some of these measurement gaps. The name stands for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging. The mission is essentially a descent probe that will plunge through Venus's atmosphere from the top to the surface, sampling and analyzing the atmosphere at every level, measuring the isotope ratios and chemical composition with unprecedented precision. The reason this matters for our central question is that the isotope ratios Da Vinci will measure are sensitive to the history of atmospheric evolution. By measuring the exact values of deuterium to hydrogen, xenon isotopes, neon isotopes, and several other species, Da Vinci can help distinguish between different histories of atmospheric loss. A Venus that lost its water early and rapidly, perhaps in connection with a catastrophic event, should have a different isotopic signature than a Venus that lost its water gradually over billions of years. The specific ratios that get measured can help determine which history is more consistent with the observations. This doesn't directly tell us about the rotation history, but it tells us about the atmospheric history, which is coupled to the rotation history through the mechanisms we've been discussing. A rapid early loss of the primordial atmosphere may be connected to a giant impact, would suggest the impact hypothesis gets support. A gradual loss over time, with specific signatures consistent with thermal escape driven by solar heating, would support the slow physics picture. Da Vinci will also descend through the atmosphere and collect data on the structure, temperature, pressure, and wind patterns at all altitudes. This will help refine our models of atmospheric dynamics, which feed back into our understanding of the coupling between the atmosphere and the solid planet, which feeds back into our models of rotational evolution. The mission won't resolve the spin mystery on its own, but it will fill in several important gaps in our picture of Venus's current state and evolutionary history. The timing is important. Da Vinci is currently targeted to arrive at Venus in 2031, which means we have several years to wait before the data starts coming in. For a problem that's been unresolved for 60 years, another 5 or 6 years isn't much. But it does mean that the answer, if Da Vinci delivers one, is just around the corner in scientific terms. What Veritas will reveal. Alongside Da Vinci, NASA is developing the Veritas mission, which stands for Venus, Emissivity, Radio Science, INSAR, Topography, and Spectroscopy. This is an orbital mission designed to map Venus's surface and interior in much greater detail than has ever been done before. Where Da Vinci will sample the atmosphere, Veritas will chart the planet. The scientific goals of Veritas include producing high-resolution topographic maps of the entire surface, measuring the gravity field at fine detail, characterizing the composition of surface materials through infrared spectroscopy, and monitoring for signs of active volcanism or tectonic deformation. All of this data has implications for our understanding of Venus's rotation history, even though none of it measures rotation directly. The gravity field measurements are particularly important. The way mass is distributed inside Venus affects the planet's response to tidal forces, which is a key parameter in the slow physics models of rotational evolution. Better gravity data means better constraints on the tidal response, which means better constrained models of how the rotation has evolved over time. This doesn't uniquely solve the problem, but it narrows the uncertainty in the models that are trying to explain the rotation. The topographic data will help us understand the history of volcanic resurfacing in more detail. If we can pin down exactly when different parts of the surface were formed, we can reconstruct the sequence of events that erased the ancient record. This might help us understand whether the resurfacing was a single catastrophic event or a gradual process, which has implications for the thermal history of the interior, which affects the rotation evolution. Veritas is targeted for launch in the early 2030s as well, arriving at Venus around the same timeframe as Da Vinci. Together with the European Space Agency's Envision mission, which is also planned for that timeframe, the next few years will see a coordinated effort to study Venus at a level of detail that has been impossible until now. The combination of atmospheric sampling, orbital mapping, and radar imaging should produce a quantum leap in our understanding of the planet. Will it resolve the spin mystery? Probably not definitively. The evidence we need to uniquely reconstruct the rotation history is, in some cases, fundamentally unavailable. The ancient crust is gone. No moons exist to serve as witnesses. The magnetic field record is absent. But the new data will narrow the range of possible histories, eliminate some hypotheses, and strengthen others. We'll come out of the 2030s with a much better understanding of Venus than we have now, even if we don't have a single confident answer. The real conclusion. So here we are, after 60 years of trying to figure out why Venus rotates the way it does, with multiple viable hypotheses, no definitive answer, and a planet that has systematically erased the evidence that could resolve the question. What do we actually conclude from this? First, we conclude that Venus is a reminder of how hard planetary science actually is. When you can't go there, when you can't sample the interior directly, when the planet's own geological processes have destroyed the ancient evidence, you're left trying to reconstruct a complex history from limited data. Every hypothesis has to fit not just the available observations, but also the physics and the broader context of solar system evolution. No hypothesis for Venus's rotation is simply wrong. They're all consistent with some subset of the data and inconsistent with others. Distinguishing between them requires evidence we don't have. Second, we conclude that Venus is a test case for how we interpret exoplanets. We're now discovering planets around other stars by the thousands, and for most of them, we have less data than we have for Venus. If we can't fully reconstruct the history of a planet in our own solar system, what hope do we have of understanding planets we can barely observe directly? Venus is a reminder that the properties of a planet are not determined by its formation conditions alone, but by billions of years of evolution that we may not be able to reconstruct. Every exoplanet we observe is the end state of a complicated history, and our interpretation of those observations has to account for the fact that the same observations can be produced by very different histories. Third, we conclude that the solar system itself is less understood than our confident diagrams suggest. The diagrams you see in textbooks, with the planets neatly arranged in their orbits and all spinning obediently in the right direction, give the impression of a well-understood, orderly system. The reality is more complex. The solar system was chaotic early on. Planets may have been lost. Orbits may have shifted. Rotations may have been reshaped by events we can't reconstruct. The current calm configuration is the end state of a turbulent process, and the details of that process are still being worked out. Fourth, and most importantly, we conclude something philosophical. Spin is not just a property of a planet. Spin is a record of history. When we look at a planet's rotation, we're looking at a fossil of its past, encoding information about its formation, its interactions, and its evolution. Venus's spin is a fossil we can't fully read. It tells us something happened, but we can't tell exactly what. It's a palimpsest, written and rewritten over billions of years, with the earliest layers scraped away by volcanic resurfacing and atmospheric turnover. This has implications for how we think about other planets. How many of the thousands of exoplanets we've discovered have histories we'll never be able to reconstruct? How many have rotational states that encode events we can't see? The assumption that we can infer a planet's history from its current properties is, in some sense, an optimistic assumption. Venus tells us that the past is, for many planets, unreachable. We can know what a planet is now, but we can't always know what it used to be or what happened to it along the way. And yet, we keep trying. That's the other lesson. 60 years of work have not resolved the Venus spin problem, but they've dramatically deepened our understanding of it. We've gone from, we have no idea, to, we have several well-developed hypotheses, each with specific predictions, each falsifiable in principle by future observations. That's progress. Not the kind of progress that gives you a clean answer, but the kind of progress that refines the question and sharpens the tools you'll use to eventually answer it. Science, at its best, is not about reaching certainty. It's about reducing uncertainty. And on Venus, we've been reducing uncertainty steadily, even without resolving the core mystery. The missions of the 2030s will reduce it further. Da Vinci will sample the atmosphere and give us better isotope data. Veritas will map the surface and interior and constrain the tidal response. Envision will provide complementary radar imaging. Together, these missions will eliminate some hypotheses, strengthen others, and probably raise new questions we haven't thought to ask yet. That's how planetary science works. You look, you measure, you model, you look again. You narrow down, you refine. Eventually, sometimes after decades or centuries, you converge on an answer, or you realize that the question needs to be reformulated. The planet next door is a reminder that we don't understand planets as well as we like to pretend. It's sitting right there, closer to us than any other major body except the Moon, wrapped in its thick atmosphere, spinning backwards at walking pace, a monument to everything we still have to figure out. And when the next generation of missions arrives and starts sending back data, we'll know more than we do now. But we might not know everything. We might never know everything. The past of Venus may remain, in some fundamental sense, unrecoverable, which leaves us with a final uncomfortable question. If we can't reconstruct the history of a planet this close to us, with all our instruments and all our theories, how confident should we be about our reconstructions of anything further away? The universe is full of planets, stars, galaxies, each with their own histories, each shaped by processes we can only partially observe. Venus is teaching us that appearances can encode multiple histories, and that distinguishing between them is sometimes beyond our reach. Every time we look at a distant world and confidently describe how it came to be, we should remember Venus, and remember that the planet next door has been refusing to tell us its story for 60 years, despite everything we've done to try to get it to talk. Maybe the most honest conclusion is this: Venus is a planet that will probably never fully confess. Whatever happened to flip its rotation, slow it down, or tilt it over has been buried too deeply for us to uncover. We will piece together a story that fits the available evidence, and it will probably be approximately right, but the actual events of 4.5 billion years ago are mostly lost. And if that's true for Venus, then it's true for a lot of worlds. The universe contains more hidden histories than revealed ones. We're going to have to get used to that. Maybe that's the real payoff here. Not an answer to the question of why Venus spins backwards, but a sharper appreciation for how much we don't know and how much we may not be able to know, even in our own backyard. Science is supposed to make the universe comprehensible, and in many ways it does, but it also, occasionally, shows us the limits of comprehension. Venus is sitting on that limit, spinning the wrong way, waiting for us to either figure it out or admit we can't. For now, the best we can do is keep looking, keep measuring, keep building models and testing them and rejecting them, and building new ones. Da Vinci is coming, Veritas is coming, Envision is coming. The 2030s will be a decade of Venus science unlike anything we've had before. Maybe the answer is in there somewhere, waiting for better data to reveal it. Maybe it's not. Either way, we'll know more than we do now, and that's worth the trip. The planet next door is spinning backwards. We don't entirely know why, and as long as we don't, it remains one of the most beautiful, stubborn, frustrating, unsolved problems in planetary science. A problem so old, it predates most of the people currently working on it. A problem so deep, it touches questions about the earliest solar system, the nature of planetary evolution, and the limits of what we can reconstruct from the present state of a system. A problem we will almost certainly still be discussing in another 60 years, possibly with more data, possibly with new frameworks, but probably not fully resolved. Venus is Earth's twin, made of the same stuff in the same place at the same time. And Venus is nothing like Earth. That contradiction is sitting 93 million miles closer to the Sun than we are, spinning patiently in the wrong direction, telling us that planetary physics is harder than it looks, and that history has a way of hiding itself. The missions are coming. The data is coming, but the universe has already taught us a humbling lesson through this one planet. Whatever we figure out next, Venus has already shown us that the simplest questions sometimes have the most obstinate answers, and that the planet next door, the one we thought we understood, has been quietly telling us for 60 years that we don't. Thanks for coming with me on this one. I hope you can't quite look at Venus the same way again.